Now, I want to talk a little bit more about your eye and light. I told you that your cones detect the wavelength of of the light. Now, wavelengths go in a lot of different, have a lot of different, uh, lengths to them, or different, um, yeah, sizes of length. If you look at that top line with the big arrow, you'll notice that the wavelengths of light include things like AC circuits, radios, microwaves, infrared. We humans do not have the ability to see any of those. On the other side, light also includes ultraviolet rays, X-rays, gamma rays, and cosmic rays. And your eyes also do not detect any of that. We only detect what is called the visible light spectrum, which is a little bit in between infrared and ultraviolet, but that includes every color that we see, um, from reds to high blues. Technically, you don't sense purple. Purple is a color that your brain makes up, but that's a little bit more complicated. It's just there's no real wavelength that is purple. Your brain just kind of makes it up. Um, Now, there are animals that can see further into the light spectrum. Famously, flies can see into the ultraviolet rays. Um, there is also some suggestion that some women, because of a difference in um, genes, can actually see a little bit more color than the rest of us can. And of course, we know that some of us are colorblind, and people who are colorblind see fewer colors. Most people who are colorblind do not see in black and white. They would have to be missing every cone in order for that to happen. And that's very rare. Usually, people who are colorblind only are missing some version of one color, or one difference in color. Now, I told you that the wavelength determines the hue. A long wavelength, like the one over here, will create reds, whereas short wavelengths are going to be seen as blue. Now, the amplitude, that is how tall that wave is, that's going to determine how bright or dim it is. Your rods detect the amplitude. And if you have a long wavelength that has a short amplitude, that's going to give you a dark red, maybe even into the burgundies, or a very crimson type of red. But if you have a very big amplitude, a tall amplitude, then that's going to be a lighter red, closer to the pinks. For the blue, if you have a short wavelength with a short amplitude, that's going to give you a dark blue. And if you have a short wavelength with a long amplitude or a tall amplitude, that's going to give you a lighter blue, maybe a baby blue. It's this mechanism that makes you perceive the sky as blue. The sky isn't blue. There's nothing in the sky to make it blue. Um, what's happening is that the light from the sun is entering our atmosphere. And as it enters our atmospheres, it bends, it refracts. And the refraction of the light, when that happens, uh, it makes the wavelengths look shorter. And in making it look shorter, well, then it gives you a blue, because of course it's the sky. If it's daytime, if there's a lot of sun, then you're going to see a very light blue. The refraction, if you've ever maybe taken a stick and put it inside of water, inside of a pool, um, it looks like the stick has bent. Um, that's refraction. because the light is entering the water, and as it enters the water, it bends again, it refracts. And in doing so, it creates this illusion that that stick has bent. Well, that same illusion is happening in the sky, but it's not a stick up there, it's just the change in that wavelength. And so you perceive that as blue. If you wait until it is dusk or dawn, you see the opposite effect. Now, instead of the wavelength looking shorter, now, as that light is entering the atmosphere, the wavelength looks like it's longer. And so now the sky looks red or orange. All of those are illusions created by your eye perceiving a short wavelength or a long wavelength.